We have another example problem here. I pulled this from our textbook. A circular loop made from a flexible conducting wire is shrinking. Its radius as a function of time is r equals r naught e to the negative beta t. The loop is perpendicular to a steady, uniform magnetic field B. Find an expression for the induced EMF in the loop at time t. So we have a region where there's a magnetic field, and we have a loop of wire that somehow we're able to change the radius of this wire, or loop of wire, I should say, as time goes on. So the radius of this loop is described by this equation. R naught would represent the initial radius of the loop, and then this exponential function is describing that the radius is exponentially becoming smaller as time goes on. The magnetic field in this area, they tell us it's perpendicular to the loop, so that means it either points straight into the screen or straight out of the screen. It doesn't ultimately matter whether it's in or out. What matters is that we know it's uniform. Why that matters is because the flux will be simply B times A. If the magnetic field is uniform everywhere in the area, then we don't have to integrate to find the flux. So the field times this area, because they also told us that the field that's perpendicular is uniform. So this term, induced EMF, should always take us to Faraday's law. Faraday's law describes and tells us that the induced EMF in a loop or coil is directly related to the rate at which the flux is changing. So here, the flux is changing in this case because the area is changing. So we need to write this magnetic flux in terms of time. We're already told that B is uniform. That means that is a constant. We know area of a loop is going to be pi r squared, but it's this radius that is changing with time. So if I plug in this function for r, and then I square it, since area is pi r squared, I don't know if you recall, if we take a power to a power, we just multiply those powers together. So once we've plugged in r as the function of time in there, we now have our flux in terms of time. These quantities are all constant because they tell us B is uniform. So that's a constant value. R naught represents the initial radius, so that would be a constant value. The beta would be constant, but time, that's what is changing. So as the time changes, the radius changes, which in turn means the flux is changing as well. And we need, for Faraday's law, to take the derivative of that flux equation as a function of time. So we'll have the B, the pi r naught squared. The derivative of an exponential function is the same function multiplied by the derivative of its power. So in this equation, we end up with 2 beta represents a constant. It's going to represent how quickly this radius is decreasing, it represents something different than B. B is the strength of our magnetic field. So this flux is going to be changing with time still. This is the rate at which the flux is changing. So the expression, or our equation that represents our EMF induced in this loop, number of turns. And if I go back to the problem, it tells me a circular loop. That to me implies N is 1. We need to multiply that by the derivative of the flux. Now we're taking it the magnitude. I don't need to include the negative sign here since we're putting in the magnitude. So just copying over what I calculated for the derivative. So the EMF induced at any given moment in time is equal to, all of this first stuff is a constant. Any given circular loop will have a specific beta value. There is a specific magnetic field. It has a specific starting radius. And then the time comes into play based off of plugging t in to that exponential function power. Now we don't get a specific numerical answer here because they did not give us values for how strong the magnetic field is or what the initial radius was. But now we have an equation that we've already solved that we could plug any initial conditions in and come up with an answer. And so this is what they were representing. This is our expression. This is how we would calculate the induced EMF in this loop at any moment in time.